But what's happened now is there's now evidence that the Space Telescope and another measuring instrument is sent back to confirm her theory that there are ancient black holes. So this woman's incredible, Priyamvada Natarajan.
Thank you so much, Paul, for that very kind introduction. I'm delighted to be here, which is my 4th visit to the Liberty Science Center. And as I say every time, I wish I had a place like this when I was a young kid. Sounds like such a wonderful resource. So today, I want to talk to you a little bit about how the first black holes came to be and what sort of evidence we now have from James Webb Space Telescope, which is allowing us to see farther and farther back in time. But before we go there and we dive right into black holes, I would like to start off by giving you a bit of a sense of how far we've come in terms of our understanding of the cosmos. Zach, could we have the first slide, please? So one probably imagines that ever since Homo sapiens could stand upright and look out at the night sky, we were trying to make sense of the sort of cosmic order, night and day seasons. So one of the earliest depictions of the night sky is the Nebra sky disk, and it's dated back to about 1600 BC. It was unearthed in the Saxony-Anhalt region in Germany. It looks like the Pleiades star cluster, the sun, the moon. We have no idea, this is a copper plate, so we have no idea why and what they were doing with this, except that it probably represents the first set of astronomers who recorded what they saw in the night sky. This is one of the earliest objects that we have. And then we move on to one of my favorite civilizations. This is the Mesopotamian civilization. So this is a cuneiform tablet dating back to 700 BC in the British Museum. And what you find here etched are actually the locations of the planet Venus. They already knew there was a difference between a planet and a star, which is just remarkable. And these are very accurate. So this script has been deciphered, and we know. Then let's jump right out to 1375 AD, by which time we still didn't have telescopes. This was all naked eye astronomy. But at this point, we had a sense of divine order. So there was always this idea that there was an agent, there was God, who created this panoply of phenomena, cosmic phenomena. However, this particular map is one of my favorite ones from the Catalan Atlas. The reason it's the favorite is it's the first one in which you can see, this laser pointer is working. Let me try the other one. It's the first one where you see an instrument, the astrolabe. So you have these 4 angels standing at the corners who are holding an astrolabe. So the first time that the idea of making measurements with instruments is depicted in a map. Of course, this map does not represent what we know about the cosmos even a couple of hundred years later. As you all know, the most fundamental shift in our cosmic view likely started. I say started because I want to show you the shifts that have come since, which have been even more radical, if you can imagine something like that. So this is when Copernicus in 1543 changed the pivot from the Earth to the Sun for our solar system. And remember, at this time, the solar system was the entire universe. That's all we knew. And so this, once again, is prior to telescopes. Of course, in 1600s, Galileo turned a spyglass upward into the night sky, and so began the era of telescopic observations. And since then, we've been building better, bigger, more accurate instruments that are allowing us to map the sky. The next slide, please. So let's now move to what the first sets of telescopes helped us uncover. So this is 1924, the astronomer Edwin Hubble was able to show, so this is, remember, we had a sense of the solar system and the idea that we were embedded in a galaxy, the Milky Way. It was unclear if there was anything else in the universe. And in 1924, Hubble showed that M31, the Andromeda galaxy, was actually another galaxy in the universe. So he expanded our cosmic view and said, it's not just us, there's another galaxy in the universe. And very soon, people began to realize, astronomers began to realize that there are actually many more galaxies, not just us and Andromeda, but the universe is actually filled with galaxies. And it was once again Hubble in 1929 who mapped out something quite incredible, which is, so this is a graph of the speed of galaxies nearby, how fast they're hurtling away from us as a function of the distance from us. And so this actually showed that galaxies are farther away they are, the faster they are hurtling away. The only way to understand and make sense of this, given that we are not in a special location in the universe, we are, we could have been any other galaxy, so we're not in a special place, we're not the center, the universe has no center. So the only way to reconcile this was to realize that this showed us that the universe is expanding. So we have this other shift in our cosmic view that now from a tidy, steady universe, the universe gets unmoored now, which was pretty radical. And if you thought this was radical, many more radical things were to come. So in 1998, as recently as 1998, it was realized that the universe is not just expanding at some constant speed, but is actually accelerating. The expansion is accelerating. And that tells you in order to effect this acceleration for the universe. And the way to think about it is instead of the distances between galaxies increasing, the increase is actually accelerating, right? And in 1998, there were two groups, large astronomy groups, and it's an absolute pleasure today to give a shout out to one of my colleagues, Saurabh Jha, who was involved in this discovery. So they realized that, this was a remarkable result. So if you thought this unmooring was disorienting, this was truly discombobulating. Next slide, please. So this is to give you a better sense. So this is what Hubble saw. This is just constant expansion. Gives you a feeling for what it is like when the distances between galaxies is steadily increasing. And in the next animation, you'll see what an accelerating universe in which the expansion is accelerating actually looks like. You can actually discern them by eye. This is a very cleverly done animation, and I'm grateful to the Liberty Science Center graphics folks, and Andrew in particular, for showing this so beautifully. So along with this, could we go back to the previous slide, please, with the contents of the universe? The other thing that we mapped out, aside from the accelerating expansion of the universe, was the full inventory of the cosmic inventory. So this is the pie chart, and the discovery of dark energy. It was clear that this is a component, likely a property of space. We don't know what it is. And that constitutes the bulk of the contents of the universe. And whatever we are made of, all the atoms that we are made of, everything in the periodic table is about 5% of this inventory. But there's more matter. Other than us, there's other kinds of matter, more exotic matter. Once again, we don't know what it actually is made of, but we know it exists. We have proof, and that's dark matter. This is the green pie wedge that you see here. So as you can see, most of the universe is actually unseen. And so for me, this has been the fascinating aspect in cosmology and astrophysics. I've always been seduced by these unseen entities. And over my career, it's become very clear that these unseen entities are extremely significant. And in fact, they shape the universe. So you might think, hey, how come black holes don't make an appearance here? You know, they're really, really tiny. So they really do not constitute a huge portion of our universe. Yet we will see today that they play a starring role, not just in shaping galaxies, but in setting the stage for everything that we see in the visible universe. So shall we move 2 slides forward, please? And so the other thing that we do know, aside from the constituents of the universe, is the timeline for the universe. We know that the universe came to be, likely emerged very, very early on, precisely 13.8 billion years ago. And it was hot, it was very dense. And we have conclusive proof of the fact that you had a hot, dense beginning, which we refer to as the Big Bang. And we have proof from this cosmic microwave background radiation. We are all bathed in this radiation, which is the ancient relic of light from the very early universe. So now we are in a situation, we've come really far from the Nebra disk, right? So we as humans have figured all of this out. We know the inventory of the universe. We know how the universe likely formed, evolved, how galaxies formed, how they evolved. So we have a very, very good understanding. And you might say, oh, this all sounds really impressive. I think the reason this is even more impressive than it seems at first is because, remember, we don't actually know what dark energy and dark matter are. We know what they do in the universe. We know what role they play in the universe, but we don't know their true nature. And the fact that we can make so much progress with those 2 big unknowns is really remarkable. Next slide, please. So I think what we really, as I said, we've pegged the timeline of the universe. Most likely, there's sort of a twiddles because it's not absolutely accurate. And we are really hoping that JWST might give us a sharper view of the first stars that form in the very early universe. And this is the reason we built JWST, because we wanted to cut through the dust in the very early universe and see the first stars as they turn on and they light up the universe. And JWST so far is delivering, and it is giving us an unobstructed view of the very, very early universe. Next slide, please. Along with the first stars, we are, of course, really excited about the fact that the first galaxies that JWST is slowly uncovering for us seem to also harbor black holes in them already. Before I tell you a little bit more about what we think when the first black holes and the first galaxies form, just want to point out that we actually do have pegged the timeline for the entire universe. Well, there's a little bit of an issue here with the 2nd decimal place that is still contested, very active research area. So the age of the universe is about 13.7, 13.8 billion years. Next slide, please. So as I said, we have a really good understanding of how structure formed in the universe, what dark matter does. Dark matter offers a scaffolding within which galaxies form, stars form. What you're seeing here are some state-of-the-art simulations, computer simulations. This is dark matter. This is streams of dark matter. And these cocoons become the regions within which gas falls in. And that's what you're seeing here in this movie. This is gas falling in. And so you can sort of see the formation of a spiral galaxy. And there, once again, you are seeing a zoom in of the way the stars are forming. So you see stars forming, some of them going supernovae, exploding. Those are the red bubbles that you're seeing. So this is just to give you a feel that we actually have a really nice storyline for the entire universe, as well as a really good understanding. It's by no means complete, many open questions. So those of you who are young here and looking for careers, there are many exciting problems to work on in galaxy formation. But we have a pretty good idea of what's really going on in the universe. And we know this across cosmic time. So we are able to predict what a telescope like James Webb is likely to see once it spears out. So next slide, please. So before I tell you a little bit about the black holes that we've discovered, it would be remiss of me to point out that black holes have always been fascinating and enigmatic, partly because they started out as a mathematical concept. Nobody believed, including Einstein, whose theory, this is these are solutions to one of his sets of equations in the theory of general relativity, which actually showed that the contents, the shape of the universe, and the fate of the universe are intertwined. He also showed that matter and space, gravity emerges from the interplay of matter and space. So matter creates changes in the shape of space. The presence of matter causes little divots. If you think of, the universe as a sheet, and if you had no matter in the universe, it would be completely flat. However, if you had, for example, something like the sun, right around the sun, you can see space is really bent. And this bending is because of matter. This is what matter does. This is a property of the way in which space and matter interact. And this is how gravity comes to be. So this, unlike Newton's laws, Einstein was able to explain the origin of gravity. And he went further than that, right? Was able to show that how tightly packed the mass is in an object determines how much of a dent you make in space-time. So you have a neutron star that is much denser than the sun. And notice how strong the deformation in space-time is. So it turns out that black holes, which are exceedingly compact, massive and compact, are actually cause a deep puncture in space-time itself. And that's one of the reasons, right? So this is a very peculiar, bizarre, and tantalizing mathematical entity. Luckily for us, it did not remain a mathematical entity, and the real universe has these black holes. Next slide, please. So some of the enigmatic, I keep saying, oh, they're enigmatic, they're tantalizing. The reason is that the gravity around a black hole is so intense because the matter is so compact, it has so deformed space. And remember, this is the entire universe we're talking about. We're not talking about, above this or below this, right? So the sheet is the universe, and these deformations are caused in this sheet. So one of the reasons we have all been intrigued by black holes is how they impact light rays. So there is a region, a sacred boundary called the event horizon of a black hole, and that demarcates the region where the impact of the dramatic change in shape of space induced by the black hole has very different effects. So if you have a light ray that plunges through the event horizon, it will never make its way back. So not even light can escape a black hole. That's how intense the gravity is. However, right outside the event horizon at twice the distance or so, 1.5 to 2 times, if a light ray hangs out there, it will be in eternal limbo. It could be captured here, it will be going round and round. And then you could have light rays that kind of graze past and go and escape. So you can see that the presence of a black hole is going to fundamentally distort light. And this is something was potentially observable, right? It looks like, hey, if the black holes are real, we should be able to see something like this. Next slide, please. So now the question is, so this is a beautiful animation showing you how light rays behave around a black hole. So black hole is shown here as a dot. And what you see is the deformation in space-time and the changes. So you see this deep divot out here. And it turns out that if light was really deformed and black holes were real, you should be able to see certain kinds of shadows. And many of you may remember from 2019, the Event Horizon Telescope collaboration for the first time mapped this shadow of a black hole. Of course, well before 2019, we knew black holes were real. Since the 1960s, we knew that black holes corresponded to real objects in the universe. They were not just a mathematical solution anymore, they were real. And in fact, we also knew how they likely formed. And one automatic way by which they formed, next slide please, was from the end states of stars. Next slide please. These donuts you have all seen, right? They were all the front page of almost all newspapers in the world. So you might ask, okay, where do black holes reside in the universe? It turns out pretty much every galaxy, including our own, harbors a supermassive black hole in its center. A supermassive black hole is something that's about 1 million times the mass of the sun or larger. And so this shows you, this of course is an artist impression. Remember, but you've already seen that picture of the black hole. You've been as up close as you can ever get with the Event Horizon Telescope already. But there are lots of phenomena around black holes, like these jets, for example, jets of material that are pushed out, powered by the black hole, that we see, but we don't fully understand quite yet. Next slide, please. So we now know that these black holes are ubiquitous. So the question of how they formed, how can you pile 1 million times the mass of the sun into a very, very compact, dense region and have it land in the center of a galaxy was a big, fundamental, open question. One thing we knew is when very massive stars live their lives out, they live a dramatic, short life, the most massive stars, and leave behind this glamorous corpse, which is a black hole. But they're tiny. Those black holes are really tiny, the end states of stars. Now, the question is, of course, you could start out with a black hole that is a remnant of a star, the corpse that's left behind, and it can grow over time. And perhaps that's how the black hole at the center of our own galaxy, which is 4 million times the mass of the sun, likely formed. So it turns out that in order to understand how black holes really formed, we need to dig a little bit deeper in terms of how they reveal themselves. How else could we study them? What are the other phenomena? We just saw some jets, we saw the bending of light. So it turns out that when black holes actually grow, they grow by gobbling gas. They sit in the centers of galaxies, they gobble gas. Any gas that comes close gets sped up, pulled in by the intense gravity of the black hole, gets heated up, starts to glow. So it turns out that X-rays are put out by an accreting or growing black hole. So growing black holes are referred to as quasars. So you have a black hole that's sitting there. These are extremely bright objects that can actually outshine all the stars in the galaxy. That's how bright they are. And these objects are seen out there, beacons in the universe, they're lighthouses of the universe. You see them way out, as far out as we can see at the moment. So these are our best shot finding bright quasars, if they exist in the very, very early universe, is going to really tell us something about how black holes form. Are there more ways than one to form black holes? Are stellar corpses the only way to form black holes? And then you have black holes like the one in the center of our own Milky Way, which is actually doing nothing. It's not really feeding. So it's a fasting black hole. This one's feasting, and that one's fasting. And we actually see both kinds, right? So we see some black holes in the universe that are really even binging, so extremely bright quasars. And then we see some that are just sort of sitting around, where basically they're sitting and they're kind of bending light, but they're really not feeding, they're not really growing in size or mass. Next slide, please. So I'm just sort of giving you a glimpse of all the ways in which we've been able to uncover the presence of black holes. So this is a beautiful animation of recent data taken in radio wavelengths. So as you all know, in the electromagnetic spectrum, radio wavelengths are the longer wavelengths, less energetic. The X-rays are the short wavelengths, highly energetic. And then we have visible light in between. So this is from Meerkat, this radio telescope. And what it reveals, could you turn on the animation, please? This is the mapping out the center of the Milky Way. It's another view of the black hole in the center of the Milky Way. So just to show you that, every wavelength, it turns out, black holes do reveal themselves, be it in the X-ray, or in the optical, in the visible as quasars. And here you see this really messy tangle. These are magnetic fields. So you see a lot of magnetic fields that are threading this region around the center of our galaxy. To give you an idea, we are sort of outside this region. So that little postage stamp would have fitted right in the center. Next slide, please. So we've seen now that black holes can be mapped out in various kinds of light. Another way in which a black hole can be mapped out is from its intense gravity. So this is real data, and the timeline that you see there is actually the year the data was taken. This is data from Andrea Goetz's group in UCLA, and these blobs that you see moving around are actually stars in the center of our galaxy. And so these are stars that are skirting around the black hole. Remember, they are outside the event, well outside the event horizon, so no fear of being gobbled by the black hole. But they are sort of skirting, moving around, and they are held together by the gravity of the black hole. And you can see some of them are actually on orbits that are really close. These are sort of ellipses, the way we see planets in our solar system, where the sun is really the focus, the most massive objects whose gravity is really holding everything up. So similarly, we were able to map the motions of these stars and infer that the gravitationally significant object, just like the sun in our solar system, is actually a very compact object sitting here where the star is. And it turns out that is Sagittarius A. That is where that donut is mapped. And so this is the black hole. So this is yet another way in which we can map out. This is, of course, further away out from the black hole compared to the event horizon image. Next slide, please. So the question is, how do black holes actually grow? Before we get to the fundamental question of how they form, we want to know how do they really grow. So as I mentioned already, we think, so the black hole is sitting here. This is a cross section. This is a slide, a cut where you can see gas that is flowing into the black hole. So black holes grow by feeding on gas that is available in the centers of galaxies. Remember, gas is a fundamental. When I say gas, I really mean hydrogen mostly. And that's a fundamental constituent of our universe, because this is the gas which cools fragments and forms stars. And it is the same gas that also in the centers of galaxies gets fed into the central black hole. Next slide, please. And the other way that we know black holes grow, remember, we are looking for all kinds of signatures that we can go and say gotcha to these black holes. So these are two galaxies that both harbor, like our Milky Way, black holes in the center, and they're flickering because they're actually feeding. This is a very beautiful computer simulation this was PhD work of one of my former graduate students. And what you see are these two black holes that are at the center of these two galaxies that are crashing into each other. They actually merge. They collide, they merge. And it turns out when they collide and merge and form a bigger black hole, they don't form a black hole that has the mass that is simply the sum of the two. slightly less than the sum of the two. And that's because some of that energy, remember mass is energy in the universe, some of that comes out as gravitational waves. And what are gravitational waves? They're basically tremors in that space-time that we saw. And these gravitational waves have been detected for the merger of stellar mass black holes. So these remnant light black holes that I told you, we've detected that. They were detected by the LIGO collaboration quite recently. However, the merger of these supermassive black holes that will cause a tremendous earthquake, if you will, in space-time, a tsunami, is yet to be detected. And that is a window that's going to open in a decade or so with a planned mission called LISA. Next slide, please. So there you have it. We have figured out all the ways in which we can uncover the presence of black holes and their properties. So let's now go back to the fundamental question. How do black holes form in the first place? So the standard story I told you is you could have POP3 refers to the first generation of stars that form in the universe. We're talking about the original black holes, right? The origin, like the first black hole seeds. How did they form? So it turns out you have a first star. It's really massive. It's about 100 times the mass of the sun, the star. And it leaves behind a black hole, a remnant black hole, a corpse that's maybe 10, maybe 100. So if you have a star that is 500 times the mass of the sun, that could leave maybe something that's 100 times the mass of the sun. It's a lot of uncertainty. We haven't seen one of these yet. So this is pretty well understood physics, however. But then in 2005, 2006, what started happening was we were starting to find these quasars, these very bright accreting black holes, earlier and earlier in the universe. We were finding black holes. From the brightness of the quasar, you can infer how big the black hole has to be from its feeding. And we discovered that there were black holes that were 1 billion times the mass of the sun, already in place when the universe was 2 gigayears, 2 billion years after the Big Bang. That's still, that's far back. It's not quite as far back as we are able to reach today. But in the early 2000s, that was pretty remarkable. So those were the most distant objects. And they seem to already harbor these behemoth black holes. The question is, really, do you have time to start from one of these over 2 billion years to get to 1 billion times the mass of the sun to power the quasars? It's pretty tight. There was not enough time in the universe to do that. So some of us, and notably with a postdoc in my research group, we started looking at other ways to make black holes with the goal that we wanted to make black holes that were more massive than these guys from the get-go. So what if, an apt analogy is, what if rather than being born as an infant, you're actually born as a 5-year-old, right? So that's the we were trying to see, is there physics that would allow us to bypass? Because remember, you have to go through a star. You have to form a star, and then you are left with a star has to die, explode, leave behind a black hole. Is there some other way? Does the universe allow you to make a black hole that is much more massive, whose birth mass is 100,000 times the mass of the sun? Could you do that? And we discovered that actually the physics allows you to do that. And so we call them these massive initial black hole seeds. So there are multiple ways. I just want to give you a feel. So this is a way the direct collapse black holes was the one that we really thought was super exciting and started working more on that. Next slide, please. Now, so that's a theory, right? So you obviously need an observation to validate. So this is a theoretical picture of how you could actually form a direct collapse black hole. So you have a blob of gas in the very early universe in a very young galaxy that starts to coalesce like a bathtub. You pull the plug out, the water goes in a vortex really, really fast. Remember, all we need to do is to funnel mass really fast, a lot of it, to a very compact region, and that's how you can get a black hole. So it turns out we were able to show that the physics will allow you to make these objects. And we were also able to show, next slide please, that there are regions in the universe where these conditions that you need actually exist to form them. So now the question is, do they form? And if they do form, is there a unique signature? Because remember, once any matter or light goes into a black hole, you lose information about how that black hole grew if you see it at a later time. You have no idea what went in when you see a black hole of a given mass and a given size. Could you play the animation, please? So we realized that there is a unique way in which you can discriminate. So this is a stellar mass black hole that forms, that slowly gobbles gas, crashes, grows by either merging into other black holes or actually grows by just simply accreting gas. Next slide, please. These direct collapse black holes form more massive to start with, and they can very easily grow into supermassive black holes in a very short time, which means the first black holes that form, they don't have a whole lot of time. If the timeline is such that you have them in place and you see them in place in galaxies very early on, then this is one viable way. And from just what I'm telling you, you can see that I keep saying, oh, the galaxy in which they form. So obviously there's a relationship between the black hole and its host galaxy, which is probably where the rub is, where you can tell the difference between these black holes. Next slide, please. So this is one possible way that we figured out, like one scenario. Okay, so this was a dream scenario. In 2017, we wrote a paper elaborating on this dream scenario. We'd been working for decades on this. So you have a satellite galaxy, gassy galaxy that hasn't really formed stars. You have a parent galaxy. Could you start the animation, please? And what happens, this is a very early universe. First stars have formed in this parent galaxy. Has a little satellite galaxy that's moving around. The gas forms a direct collapse black hole, as we saw before. The gas just gets funneled in rapidly. And then the satellite, as satellites do, is going to merge. Do you turn the animation on, please? This one will merge with the parent galaxy and be the central black hole for that galaxy. Remember, this is the first generation of stars. You've not formed stars all that vigorously. You've formed a lot of them, but not as many. You have an outsized black hole in this galaxy compared to one that you would have had it formed from a light seed. So there's a fundamental relationship between this host galaxy and the black hole. And we actually observe that. That's an empirical observation. In the nearby universe, we know what that relationship is. So for example, for our own galaxy, the Milky Way, the mass of the black hole is 4 million times the mass of the sun. The stars outweigh that black hole by several orders of magnitude, 6 orders of magnitude. Okay? So the black hole is really massive and compact, but its region of influence and its gravity is confined to right around the center. Once you move away from the center, stars take over in terms of their gravity, right? So in this scenario, you have something very peculiar. You have a situation where the mass of the black hole becomes comparable to the mass of the stars. The stars don't actually dominate the gravity. It's the black hole and the stars contribute equally. Next slide, please. And this is something that we knew was observable with the James Webb Space Telescope. And so here we start out, next slide please, with these heavy direct collapse black holes. And now we have this unique kind of signature. In 2017, we wrote a paper detailing all the properties. It doesn't matter what all these lines are. The only thing I want you to look at is this, the black stuff is the observability from JWST. Everything above you can see, everything that pokes out, if you do not have access with JWST instruments to see anywhere here. So here you see lines that show you these are predicted properties. This is just the energy as a function of the wavelength that is going to come from that combination of that growing black hole and the stars in the galaxy. So starlight plus the light that is coming out of matter that's falling into a black hole. So these are the predictions. So you notice these lines, the purple, the green, the orange, and the red pop up well above. So you should be able to see them, right? And the other lines are sort of confounding things. But what you see is there's a very strong feature here. There's a very sharp upturn. That is a signature. Remember, we are looking for these tiny distinguishable signatures. Next slide, please. So this was a prediction we made in 2017 of what a direct collapse black hole is likely to be. And those are, they should pop. James Webb should be able to see these bizarre objects. However, in that paper, we already noted, if we want to find the most distant black holes, we actually need help. We need help from nature. We need nature's telescopes. Thankfully, they exist to augment JWST's reach. So it turns out that another thing that Einstein's theory tells us when talking about matter and space-time, shape of space, is that because space gets curved due to the presence of matter, light rays are going to get focused and defocused like you have in lenses. So matter behaves like a lens. And literally, there are clumps of matter, majority dark matter, as we saw, and this is a cluster of galaxies. We are here, and if there is a distant object which is emitting light, the light from that object gets deflected, and it reaches us, and it does two effects happen. Next slide, please. You have that this light gives you a distorted shape of this distant object. So you don't see the real shape anymore. You see a mangled shape. And it also magnifies it. So you can imagine, so it is literally nature's telescope augmenting our instruments on the space telescope. So as I said, you mangle the shape, so you saw the original shape. It was like a fuzzy galaxy with a lot of stars. It would get mangled into this thing and magnified. And there are times when you don't get mangled, but you just get magnified. So the key effect we are after is the magnification, right? So we have these very, very faint objects because they are distant. And we want them to be magnified. So in that paper, we said, look, the optimal way to find the first black holes is if we actually look through one of nature's lenses. So it turns out that we've mapped out these regions of the universe that behave like lenses. Next slide, please. These clusters of galaxies. And in fact, this is another, dark matter. As I said, dark entities are things that I'm really interested in. So that's another sort of a region of space that I had modeled with a group of people, 6 regions that would be the most efficient lenses. Obviously, JWST was going to look through them because those are the optimal places to find the most distant objects behind them, because they'd be magnified, right? And so it turns out that James Webb, late last year, looked behind one of these objects. I mean, you must have all seen the image of a cluster of galaxies that does all this lensing. It was one of the first images released by the White House from JWST. So this is a different cluster. It's not that one, but it's a lens. And it turns out, looking through this, in February, one of my collaborators called me and said, guess what? We found a very distant, interesting-looking galaxy behind this. Next slide, please. So one of the predictions that we had made of these direct collapse black holes, these heavy seeds forming these overmassive black hole galaxies, was that it had to be seen in the X-rays as well. Remember I told you that black holes also reveal themselves. So to be absolutely sure that you have a black hole there, you need to detect X-rays. Because you could have very clumpy stars that are so bright in the early universe that you can imagine you think there's a black hole there, but you're not so sure. To be absolutely sure, you need an X-ray detection. So you need the Chandra Space Telescope. And so we had we had seized the opportunity a year and a half ago. We had said, aha, let's apply for time on Chandra to look through that same lens, look behind the same region, because obviously to find one of these direct collapse black holes, one of these really first black holes, you need this combination. This will be a unique signature. And guess what? A couple of months later, we got again earlier last year, we got the data. And my collaborator, Akash Bogdan, on a cold February morning called me and said, are you sitting on your chair in the office? And I don't know, I think I was doing some like mundane thing, or my usual, which is like just staring as my students tease me. You're staring and you seem to be in a trance, but I'm actually calculating, right? I'm thinking about something very, very hard. And he said, well, get back to Earth, hold on to your chair, and I'm going to show you we detected the object in the X-ray. Bam. So we know it's a black hole. And it's there. We can measure its mass. We can look at its properties. And we can see the galaxy. James Webb has shown us the galaxy that harbors this black hole as well. They're coincident. So it's a simultaneous observation. Next slide, please. And it turns out that it satisfied tick, 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 every property that we had predicted for this direct collapse black hole. It was overmassive. The black hole was overmassive. It was detected in the X-ray. It was it was a galaxy that looked like it had merged. Remember that satellite that's merged and collided into the parent? It all hung together, right? Next slide, please. We were pretty stunned. I mean, I was speechless. I'm rarely speechless. And and the reason I was speechless is that we had published years ago, remember these orange curves and the green curves? So this is the same graph on which the blue points are the detected object. This object called UHZ1, that is James Webb data, and this is our predicted spectrum for it. It was unbelievable. And you see, remember I told you there's a feature, you have a very sharp rise, and then you're pretty flat with a slight gradient at the top. And this was a perfect match to what we called an overmassive black hole galaxy that has to originate because of how far away it is. We had also predicted how far away these objects actually have to be. They have to be in place 500 million years after the Big Bang. It's really early, right? Very early. So this was complete serendipity that this worked out. Next slide, please. And then remember I told you that it has to be detected in the X-ray as well as James Webb. And so this is the data, James Webb data shown here. So it matches our model. And then this is what should be observed in the X-ray with Chandra. And this is the data from Chandra. So it was pretty clear that not only had we found one of the most distant black holes, one of the most distant black holes that is simultaneously detected both in the infrared as well in the X-ray. And the only way you could have something, and this is about 10 million times the mass of the sun. It's even more massive than the black hole we have in the center of our galaxy today. And this was in place 470 million years after the Big Bang. It's remarkably early to have such a big black hole in place. The only way you could really have it if it formed from a massive seed. And so we were able to show that it matched every property of that sequence that we had predicted. So we have detected not just, there will be more black holes, like I think yesterday one was announced. Most likely they've detected a black hole that is even further out. It was not detected in the X-ray. So you cannot say what kind of seed it came from. that is what is special about this object. We can actually nail the origin because of the set of properties that these massive seeds need to have. Next slide, please. But what we've actually shown beyond one object is the fact that there is more than one way to make a black hole seed. Okay? It sort of opens up this whole new discovery space of, okay, so theoretically, many people have said, well, there ought to be multiple pathways. You know, we were the first to propose that there had to be this massive one way. The satellite smashing in was one way to make these massive seeds. Now, there are other predictions about how other ways in which you could make not just direct collapse, but direct collapse, maybe that happens in slightly different contexts where you could get that to happen. So now we've opened that window, both observationally as well as theoretically. And we've fundamentally transformed our view of black holes and our view of the formation of galaxies and their black holes, because we have shown, because there's more than one way, it's much more efficient than we ever imagined. So this is just to show you how do we know it's a massive seed. So these are tracks that, you know, if this black hole that we've detected in UHZ1, if it formed from a light seed, you know, what it would take, how much time, what are the conditions it would take. These are very extreme growth conditions in order to reach the mass that we see it at. Whereas if it started life as a direct collapse massive seed, it very comfortably reaches the mass that we detect in. Next slide, please. I think I'm going over time. So I think we are done here. So I think what I want to convey to you is the excitement that not only, of course, it's a completely serendipitous discovery of this object, and that it validates a theoretical picture, and it's deeply impactful because what it does is that it really shows us that black holes are in place very, very early in the universe, and that their formation is coupled to the formation of galaxies in a very intricate fashion, and that there are multiple ways to make the first black holes. So I think I'll just stop here, and thank you so much for coming.